Good afternoon, everyone. Thanks for coming out today. My name is Andrew Lusk. I am the person who actually organized this event. I'm a liberal studies freshman here at New York University, Washington, D.C. I'm the executive manager for the DC Dialogues program, and this was kind of my brainchild, my big project for this semester, bringing together the sciences for you to see what's going on in space and time. New York University DC Dialogues is a student-led group that seeks to engage the NYU DC student cohort and the local community in key discussions on politics, culture, business, environment, education, and specifically for today, science. On behalf of the university and specifically NYU DC Dialogues, I'd like to welcome you to this incredible lecture on basic cosmological theory through the eyes of Professor Stephen Hawking, as presented by NYU's Director for the Center of Cosmology and Particle Physics and Associate Professor of Physics, Matthew Kleban, who has joined us today from New York University, New York. Matthew will begin the lecture for about an hour and a half, followed by a 30-minute break with sandwiches and refreshments upstairs on the first floor lobby. We will then return to the auditorium for a Q&A session and continue with the second half of the lecture. There will be a brief second break before a final Q&A session and program close. Again, thank you so much for coming, and please silence your cell phones. And now please join me in welcoming Matthew Kleban. Thank you.
Can you hear me? Great. Well, thanks to all of you for coming out. Today I'm going to describe some of the physics that's in Stephen Hawking's most famous book. It's called A Brief History of Time. And I'll tell you about some recent developments also in these areas, which are not in that book. Before I start, let me just say a few words about myself. There we go. So as Andrew told you, my name is Matthew Kleban, and I'm the director of the Center for Cosmology and Particle Physics at New York University in New York. That's our logo there. It's CCPP. We chose that because we had quite a number of, let's say, ex-Soviet physicists when we started. I did my PhD at Stanford, and then I went to the Institute for Advanced Study in Princeton, which is where Einstein went when he first moved to the US from Germany. This is their logo, which they're going to update, they told me the other day. So what do I do? I'm a theoretical physicist. Well, when I'm not doing administration and when I'm not teaching, I'm a theoretical physicist. And that means I don't have a lab. And in fact, I don't look very much at experimental data. So I spend most of the day reading papers, writing papers, or trying to do calculations and usually failing. So this is a kind of science which is fairly unique to physics. These days, there's such a thing as theoretical biology. That's quite new. Historically, really, physics was the only science that had theoretical scientists. And maybe the most famous example of one is Einstein. So Einstein never did any experiments. He paid some attention to data, but mainly he thought about things and wrote down mathematical equations and tried to solve them. And Stephen Hawking is another physicist like that. So he also didn't do experiments or work on data. I work on the largest things in the universe and the very smallest things in the universe. And curiously, there's actually a connection between these two. So the science of the very large is called cosmology. That's the study of the universe as a whole. And I work also on particle physics and a theory called string theory, and attempts to quantize gravity. So just to give you a sense, this is my actually old office, my former student Marjorie, and here we are trying to do a calculation and not succeeding. OK, so here's an overview. We're going to start talking just a little bit about Stephen Hawking, about his life and his work. And then we'll launch into this set of physics topics. So Hawking was born in Oxford in the UK in 1942, and in fact, 300 years to the day after the death of Galileo. He went to Oxford University as an undergrad and then to Cambridge. And very early on in his life, at age 20 or 21, he was diagnosed with amyotrophic lateral sclerosis, which is called in this country Lou Gehrig's disease. And that's a disease that's not very well understood, but it's usually fatal after a few years. And so he was told at that time that he had a few years to live. He lived a lot longer than just a few years, but he gradually became more and more paralyzed, to the point that sometime in the 80s, he was not able to speak and had lost essentially all muscular control except some part of his face. I'm not sure if it was his eye or something in his mouth that he could move, and that was it. Now, he could still operate a wheelchair through the use of this, or at least he could operate a speech synthesizer through, I think it was a wink in his eye from standing behind him. It was some muscle in his face that he had control over, but really that was it. His work, as we'll go into, was in the same general area as mine. So he was interested in big fundamental questions. So what's the nature of the universe as a whole? What was its origin? What is its fate? And how do we understand the fundamental physics that governs it? And these kind of ideas are usually in an arena where they can't be tested directly, at least not in the short term. So they are certainly subject to constraints from experimental data, but they're not the kind of thing you can go into a lab and do an experiment and try to rule out that theory or confirm that theory. Hawking's career as an academic was, let's say, meteoric. He was very young when he was appointed to the Lucasian Professorship of Mathematics at Cambridge University. And that's a very old named chair at Cambridge. It was held by Isaac Newton. Newton was the second Lucasian professor. And in '88, Hawking wrote a popular book called A Brief History of Time, which I read as a kid. And a lot of other people did as well and were inspired to learn about physics. And he died recently on March 14th, which is Pi Day, 314, and also Einstein's birthday. And here he is in an airplane that simulates zero-G by diving. And you can see he was a very adventurous soul. He was extremely determined. He wouldn't let his disability stop him. And he had a sense of fun. I'll come back to that towards the end. So Hawking made a number of important discoveries in his career. I think probably the most important, and he himself said this was his most important discovery, was that black holes, and I'll tell you more about black holes later and what they are actually not entirely black. So before Hawking, it was believed that black holes couldn't emit any form of radiation, light, any kind of particle, that they were completely black, inert objects. But what Hawking showed is that, in fact, when you take into account quantum mechanics, black holes radiate as though they were hot objects at a non-zero temperature. If you heat up a piece of iron, it glows red. Any kind of hot material will glow. It will emit light at some level. And what Hawking showed is that black holes do that too. This is not a discovery that's been confirmed experimentally for the reasons I was just saying. And in this case, it's pretty hard to have a black hole in a laboratory. And if you could, it would be very dangerous. So it's not something you can just go and check. And the black holes that we know of in the universe are very far away, and according to Hawking, radiate very little. They would be very cold. So we can't look at them and confirm his prediction that way either. But I recently gave a lecture, actually, about 3 weeks ago to my colleagues, in which I gave 7 arguments for Hawking radiation, 7 different arguments. They're all pretty convincing. They don't rely on much other than the basic ingredients that go into black holes and that go into quantum mechanics. So just about everybody in this area is quite convinced that this prediction was correct. I called it a discovery in quotes, because it's a kind of mathematical discovery. So I think it's true. And it's had an enormous impact on research in this area. And it's also closely related to something else that has been confirmed, or at least that there's very strong evidence for. I won't talk about this much, but it's closely related to something called cosmic inflation, which is the theory of the very early universe and how stars and galaxies came to be. So Hawking did much more than just that. He also proved a number of theorems in Einstein's theory of general relativity. That's our modern theory of gravity. Most of them are related to black holes or cosmological singularities in one way or the other. So in short, what Hawking showed is that when matter is collapsing, like if you have a cloud of dust or particles in outer space and it collapses under gravity, it's impossible for it to stop past a certain point. It must form a black hole, and inside that black hole, there must be something called a singularity, which again, we'll come back to later. So he proved several theorems like this, some of them with Roger Penrose as a collaborator. And he also worked on cosmic inflation, as I mentioned, and on a theory for how the universe came to be in the first place. So I first met him at this meeting. This was back in 2003 at UC Davis. So here he is in the front, and here I am, a little younger. And I met him many times since then. I actually interviewed for a lectureship at Cambridge right before I came to NYU. And the last time I saw him was on a goat farm in Belgium. So one of his former students, Thomas Hertog, lives on a goat farm, an active goat farm, and had a party for him. So we were making cappuccinos directly from the goat. And I can tell you, Stephen Hawking did not drink one. Maybe it was not a good idea, given his state of health. But in any case, he was very active. He traveled around the world giving public lectures, going to scientific meetings, writing papers, and he never slowed down, as far as I know. OK, so this is the book. This is the old edition, the one that I had as a kid. And here's the table of contents. I can't cover everything in this book in the time we have, but I'll focus on a good part of it. So we'll start off discussing the nature of space and time and what it means for the universe to be expanding. And then we'll talk about black holes and the fact that, in fact, they're not black, according to Hawking. Then we'll talk about the arrow of time and eventually a theory for the origin of the universe and what it might mean for the unification of physics. And we'll see how we do. There's going to be 2 question sessions. So please, if you have questions about anything, save them up and ask them then. So we'll see how we do in terms of time. But don't hesitate to ask in those question sessions if you have any questions. OK, so we'll start off talking about space and time. Modern science, in a sense, starts with Isaac Newton about 300 or more years ago, 350 years ago. Oops. So what Newton did is show how mathematical equations, and he invented those equations. He invented the equations and the technique you needed to solve them, could be used to predict the motions of planets and other objects near the surface of the Earth. And this caused a revolution in human thought. It sparked the Enlightenment, arguably, because all of a sudden you had someone who could solve an equation and predict with great accuracy the motion of something as far away and exotic as a planet in the sky. So that was something that wasn't possible until Newton. And his universe was a kind of clockwork universe. There was no randomness. Newton's laws were absolute. If you say where something is and how fast it's moving at some time, that's enough to predict where it will be at any future time. So his laws were deterministic, and his rules for the solar system were like some elaborate device which just moved the planets around in these predictable patterns. Space and time for Newton were an absolute frame, like a piece of graph paper or something, which is just fixed, and on top of which events happen. But space and time themselves weren't things that could change, or they weren't interesting. They were just an absolute frame in which you could describe the motion of things. And Newton is most famous for 3 things. So first of all, he invented calculus. I'm sure you all love calculus. It's an incredibly useful mathematical technique because it lets you solve equations for all sorts of things. So everything from the motion of planets to problems in industrial engineering. It's a very powerful and useful mathematical technique. And it involves infinitesimal quantities, which was the main sticking point, the reason why it took this long for it to be discovered. It involves a limit in which you think about smaller and smaller intervals. In Europe, Leibniz is given more credit than Newton for discovering this. But in any case, both of them contributed. And Newton also wrote down the laws of motion, Newton's 3 laws, that if you've studied physics at any level, you've heard of. And he wrote down a theory of gravity. He also worked on optics and a number of other topics, which are important as well. But it's for these 3 accomplishments that he's most famous. And again, this combination was so powerful that it revolutionized the world, because it showed that you could predict the motions of planets very precisely. So what did Newton's theories predict? First of all, that the planets go around the sun, not the other way around, and the Earth goes around the sun. And that the planets move in closed ellipses. So they don't actually move in circles necessarily, although that's a possibility. They move along an ellipse, like an oval. And they move with the size and shape of the ellipse is determined by the mass of the sun and by the initial position and velocity of this planet. They don't move with constant speed. They move faster when they're closer to the sun and slower when they're farther away. And all these things had been observed already by various astronomers of the time. But there was no understanding of why they were true. So it was known that planets seem to move this way, but not why, and not how you could explain that. And so Newton's theory finally settled this ancient debate between heliocentrism and geocentrism, whether the Earth was the center of the solar system or whether the sun was. It's funny to say the Earth was the center of the solar system, but that's what the debate was about. And this was a very serious debate not so long before Newton's time. Giordano Bruno was burned at the stake for espousing a theory that went against the teachings of the church. And Galileo himself was sort of put under house arrest and not allowed to talk about his theories openly. So in those days, it was dangerous to be a physicist. Anyway, that framework stayed with us until much, much, much later, centuries later, when Einstein came along. And what Einstein did is he had what's called a miraculous year, annus mirabilis, in 1905. He wrote 4 papers, each one of which would be more than enough to win a Nobel Prize, and each one of which was in a different area of physics. It's never happened again. One of the things he did in this year was fundamentally alter our notions of time and space. So according to Einstein, first of all, space and time are not really separate. You should think of them as unified into one structure, which he called space-time. And secondly, time does not flow at the same rate for everybody or for every object. It's a little bit like saying that if I take an object and I rotate it, or if I rotate myself relative to an object, you can imagine yourself floating in outer space and looking at something, so there's no obvious up or down. What you might say is the height versus the width versus the thickness of that object would change as you rotate it or as you rotate yourself relative to it. Right? If you don't have a notion of up or down, you don't know what's height and what's width and what's thickness. When time is unified with space, they mix together in a way that's sort of like that. So the duration of an event depends on the frame of reference of the observer. Now, a lot of people, when they hear this, they think, OK, this is just a question of perspective. I mean, after all, when you're excited or scared, time seems to slow down. Or if you're waiting in the doctor's office or something like that, it really slows down. Right? So a lot of people think this is just a matter of perspective. It's nothing more than that. It's not. It's a physical thing that has physical effects, which in Einstein's time were very difficult to measure, but today are rather easy to measure. Still not something you could do at home, but it's something you can do in any scientific laboratory, or even if you're a surveyor or an engineer working in certain applications. So what am I talking about? So here's a famous example. And this is, of course, not an experiment that's been done exactly like this, but I'll tell you in a moment what has been done. So imagine 2 twins, so the same age, obviously, one of whom remains on Earth, and the other of whom gets into a rocket ship, which blasts off and flies very fast through space, and then turns around or makes a big circle and comes back to Earth. If you exaggerate this so that this rocket ship goes very, very fast, there will be a very big difference in the age of these two twins when the rocket comes back to Earth and lands, and the traveling twin comes out and greets the twin that remained on Earth. This twin will be young, and this twin will be old. So this is not a matter of perspective. The biological age of these two twins will be different. Now again, this experiment is hard to do because we don't have rocket ships that can travel fast enough. And in any case, the biological age of something isn't something of a person isn't something you can measure precisely. But we have very accurate atomic clocks. So these are clocks that keep time incredibly accurately. And you can literally take two clocks, which are synchronized together, put one on a jet plane, fly it around the world, have it land again, and you'll see that less time has elapsed on the one that flew around the world. So this is done, again, it's not this experiment is done all the time because it's already been done. There's no reason to do it many times. But there's no problem in doing it. These kind of clocks have much more precision than is necessary to do this experiment. So it's something we know for sure is correct. So that was Einstein in 1905. And for the next 10 years, Einstein worked on a theory which would be even more revolutionary. And it was called, he decided to call it general relativity. This theory that I told you about with the twin paradox is called special relativity. Einstein was working for 10 years on this theory of general relativity. He understood that he wasn't done, that there was something more that he could add. And he wanted to explain gravity in a totally revolutionary and different way. So he wanted to think of gravity not as a force at all, but rather as a consequence of geometry. Einstein's idea was that space and time not only are relative in the sense that time can flow at different rates for different observers, but that space and time are some sort of flexible, dynamical thing, something which doesn't always take the same form, but reacts to the mass and the energy that's near it. So this is a cartoon which in some ways is very misleading, but it's supposed to show you that the space near a massive object like the Earth is warped, according to this theory of Einstein's. It's curved. And what Einstein said was that, so the space is curved, and objects move on the shortest paths they can move on in this curved space. So something that looks like an orbit, so the moon orbiting the Earth or a satellite orbiting the Earth, is actually the moon or that satellite going in a straight line. All right, now how can that possibly be? It's going in a circle. It doesn't sound like a straight line. Well, imagine you fly from Washington, DC to Beijing. If you plot the route of that flight on an ordinary map, it doesn't look like a straight line. It goes nearly over the North Pole on its way from Washington to Beijing. The reason it does that is not so that you can look down and see some polar bears. It's because that's the shortest distance. That's the shortest path that you can follow on the surface of the Earth from Washington to Beijing. So straight lines, how do you define a straight line? Well, the shortest distance between 2 points is a pretty good definition. Straight lines on a curved surface, like the surface of the Earth, they don't look straight. They seem to be curved. And Einstein's great realization was that maybe you could have a theory where mass and energy, heavy objects like the Earth, would change the geometry of space-time in such a way that objects actually just go in straight lines, but that mimics all of the results of Newton and beyond. It makes more predictions. So that was Einstein's idea. It worked. And again, we now have strong observational evidence that it's true. I'll mention a little bit of it in a moment. And among other things, this theory, because it predicts that space and time can react to the presence of matter and energy, it predicts what are called gravitational waves. So if I go like this, I'm moving some mass and energy around. And I'm creating a little bit of sound. You can't hear it, but there's a little bit of sound. If you stood near me, you'd hear that. Because I'm causing ripples to propagate through the air when I make that motion. I'm also creating, according to Einstein, gravitational waves, which are ripples in this fabric of space-time, which spread out at the speed of light and move away from this event. OK. I think this is the only equation in the talk, but there had to be at least one. So this is Einstein's equation, or really equations. It's a bunch of equations all together. And I'll just tell you that what it says is that geometry, so the stuff on the left-hand side of the equality here, relates to the geometry of space-time. It tells you how it's curved and how it's warped. So geometric curvature, that's this left side, equals, this is a constant, c is the speed of light, and g is Newton's constant of gravity. It tells you how strong the force of gravity is. So geometry equals some constants times this capital T is the energy of whatever's in the universe, energy and mass of whatever's in the universe. So if you have some energy or mass, for instance, the Earth, that's on the right-hand side. The left-hand side can't be 0, or it wouldn't be equal to the right. It has to be equal to something, which means the space is curved. And that's what this picture was trying to illustrate, that the space is curved near the Earth because of its mass. Now, Einstein was able to write down these equations because there's really only one set of equations you could write down. They are very close to unique. And it took him 10 years to do that because he didn't understand the correct mathematics to be able to do it. At that time, it existed, this mathematics. It's called Riemannian geometry, or non-Euclidean geometry. It's the geometry of curved spaces. So that mathematics existed, but it was relatively new. And not very many people knew about it. So it took Einstein quite a while to learn enough of it to figure out what equation he could write that would make sense. But eventually he did in 1915. And then, having written down this equation, he couldn't solve it. So one of the strange things about being a theoretical physicist is that you often have a precise theory. You have a set of equations which, in principle, tell you everything. But you can't use them because they're too hard to work with. They're too hard to solve. What do I mean by solve? Well, for example, I say, OK, I want to have the Earth and, I don't know, another planet, or the Earth and the sun. And I want to know what they're going to do. Well, I know what they're going to do. They're going to fall together or they're going to orbit. But I want to see that come out of this equation. So I put that in, and then I try to solve it, and it's really hard. The problem of just two objects orbiting each other in general relativity is so difficult that there is no exact solution to it. And in fact, it wasn't done even on a computer until about 15 years ago. There's lots of approximate solutions to it, which is a good thing. It turns out to be easy to see, well, not that easy, but relatively easy to see that these equations predict almost the same thing as Newton would have. But finding the exact thing they predict is very hard. The reason it's so hard is because of these gravity waves that I mentioned. So it's really not a problem of just these two masses orbiting each other. It's the whole space-time which can have these ripples and waves in it. Anyway, so those are Einstein's equations. They're very hard to solve. And among the achievements of Stephen Hawking was establishing some characteristics of those equations. I mentioned these singularity theorems before. So Stephen Hawking, along with collaborators George Ellis, this is George Ellis here, and Roger Penrose, and several other people, they were able to establish some very foundational and fundamental results about Einstein's equations. And remember, this was in the 70s, and Einstein wrote his equations down in 1915. So it really was a very hard problem to prove much about this. And again, many of Hawking's results are related to black holes, which we'll come to. How many of you have seen Interstellar? Yeah, more people should see this movie. It's really good. Well, I'm going to spoil it for all the rest of you. Sorry. Or at least one part of it. So there's a part of this movie where there's a moon or a small planet which is orbiting a black hole. And I feel really bad about this. Sorry about this. Some of the characters go down on this planet, which is covered with this ocean. And well, I won't tell you what happens to them. But they spend a few hours down there. And then they fly back up to their spaceship, which is orbiting around that planet. And it's further away from the black hole, out of its gravitational field, where they meet another crew member that they left behind. And a few hours have passed for these characters who went down to this planet. And many, many decades have passed for the person remaining up in the spaceship. And of course, they're all shocked and surprised by this. And in fact, in watching the movie, I immediately started calculating whether this could really happen, because it seemed like exaggerated. And it is, but maybe it could happen just barely. But as a plot device, it's great. And the basic idea is correct. Time not only flows differently for objects that move, that was special relativity, it also flows differently for objects at different heights or depths in a gravitational field. So if you spent your life high up in the mountains, you would live just a little bit longer and be just a little bit younger. Sorry, the other way around. You would live a little bit shorter. Time would flow faster for you. So you would be just a little bit older than your twin who lived down at sea level or at the bottom of the ocean or something. The size of that effect is tiny. So that, again, could never be measured with biology. But with atomic clocks, it's really easy. So again, you take two synchronized clocks, you send one up on top of a mountain or in an airplane, you keep the other one down here. Don't put it on an airplane because then it's moving, that makes it harder. Just send it up on top of a mountain, wait for a while, and then bring them back together. And they will read, there will be a mismatch between them. The one that was lower down, less time will have passed. So this is so well understood and so, well, relatively easy to do that it's even being used for a kind of surveying. If you want to know, what the altitude is at various points on Earth, this is one way you can do it. You just take a clock and you let it sit there for a while, and then you compare it to another clock somewhere else, a reference clock. So it's really remarkable that these ideas, which have still nowhere near been absorbed by most people, that time runs differently at different heights in a gravitational field. It's a crazy idea. But it's used routinely in this kind of thing. And in fact, it's integral to the GPS system. So this is some cartoon of the GPS system. There's some number of satellites orbiting the Earth. You need at least 4 of them in the sky at any time if you want to know where you are and how high you are. And the way it works is your phone or your GPS device receives signals from these satellites, and it compares the timing. So each satellite sends out a signal, and like it's noon and 1 second, it's noon and 2 seconds, whatever. It sends out these signals repeatedly. Your phone receives them, and it's receiving them from multiple satellites. And they're saying different times because the satellites are different distances away, and it takes some time for the signal to arrive. And then your phone compares these differences in time, and it can figure out where it is by a kind of triangulation. But those satellites are high up in a gravitational field, and they're moving. So actually, both of these two effects are important. And if you didn't take them into account, the whole system would cease to work within a few minutes. So these effects were taken into account by the engineers that designed this. So just to emphasize, these are not these are effects that one can easily measure and must take into account for a system like this to work. OK, so the last thing about Einstein's theory, so it predicts that space-time is curved. It also predicts how gravity acts on light. This is called gravitational lensing. We'll come back to that when we talk about black holes. It predicts black holes, and again, we'll come back to that shortly. And lastly, it predicts that the universe as a whole cannot be static. It can't just be sitting there and not doing anything. It has to be expanding or contracting. So let's explore what that means. What does it mean to say that the universe is expanding? OK. So I think the best way to explain this is with an analogy. And like all analogies, this one is deeply flawed. It's good in some respects, and it's terrible in some other respects. And the main problem with it is that it's a 2-dimensional world instead of a 3-dimensional world. If you're wondering what a dimension is, well, if you want to specify where you are, you could say, I'm at this latitude and this longitude and this altitude. Right? That says where you are. You need 3 numbers. That's because our world is 3-dimensional. But suppose somehow our world was 2-dimensional. There's a book called Flatland, which imagines this. So there is no 3rd dimension. It just doesn't exist for us. You only need 2 numbers to specify where you are. OK, except that now, if you can, imagine that although it's a 2-dimensional world, it's curved. It's the surface of a round balloon. And then you may say, well, how can you have curvature without this 3rd dimension? Fine, have a 3rd dimension. Then you're going to need a 4th or a 5th dimension to understand Einstein's mathematics. You don't actually need that but if you like it, you can keep it. So you could say there's a third dimension, but you can't get into it. You're stuck, you're stuck to the surface of this balloon, and no matter what you do, you can't get off it. You're not even aware that this third dimension exists. You just live on the surface. The surface happens to be curved. And okay, the balloon is really big, so it's hard to tell, just like people used to think the Earth might be flat, even though you can see a ship disappearing over the horizon. But people used to think the Earth might be flat because it's so big, it's not that obvious that it's curved. Same thing here. All right, so you live on the surface of this balloon. The surface is your whole universe. Now, imagine that this balloon is increasing in size. If that's happening, then if you look at a friend of yours that's some distance away, you'll see them receding away from you. Not because they're moving relative to the surface of the balloon, but just because the balloon as a whole is growing. And so the space in between you and that other person is increasing in size. So these are some galaxies or something, and they're getting gradually further and further apart. OK, now I'm sure you've all heard of the Hubble Space Telescope. That's named after an American astronomer named Edwin Hubble. And he was working in the 1920s. And back then, he had one of the best telescopes in the world. Back at that time, the US didn't have very many great theoretical physicists, but it had a lot of money to build experiments and telescopes and so forth. So he had one of the best telescopes anywhere in the world. And looking through it, he could see multiple galaxies. So here's a picture of a galaxy. So this is taken with a telescope far better than the one Hubble had access to. Hubble could just see a kind of smudge, and it wasn't entirely obvious what it was. There was some debate back then over whether it was really a different galaxy or whether it was some cloud of gas within our own galaxy. But it got resolved around that time. Anyway, this is called the Pinwheel Galaxy. It has this beautiful spiral shape. And it happens to be oriented, so we're looking at it face on. It's quite flat, like a plate, but we're looking at it face on. This is an image from the Hubble Space Telescope. It's a small part of the sky. It's a tiny, tiny part of the sky, but the Hubble Space Telescope can see very far. And you can see many galaxies in this image. There's one there, that's one, there's one over there, there's one over there. This is a star that's pretty nearby. So there's some stuff that's nearby, but there's also a lot of galaxies in this image. The universe is full of galaxies. Each galaxy has billions and billions of stars. If you're old enough to remember Carl Sagan, billions and billions of stars, and there are billions and billions of galaxies. So Hubble couldn't see this well by any means, but he could see 50, and as time went on, more like 100 or 200 galaxies. And he noticed something very strange when he looked out at these galaxies. He noticed, I lied, there's one more equation. He noticed that the further away something was, the faster it was moving. And not in some random direction, moving away from us, away from Earth. So in this equation, v is a velocity, and specifically it's the speed away from Earth. D is the distance, and h is a constant, which I'm not sure what Hubble called it, but it's now called the Hubble constant. So velocity or speed has units of distance over time. This is distance, so this has units of 1 over time, this h. So he noticed that the further away something was, the faster it was moving away from us. So here's a plot from his paper. This is distance, this is velocity, and you can see a not very linear relationship. These circles and dots are his data points. They're kind of a big cloud, so it's not a very tight line. But it's not too bad if you're used to looking at this sort of thing. A linear relationship between distance and velocity is a reasonably good fit. And I mean, notice, for instance, that, so this is 0. Anything below this line means it's coming towards us. Only the very nearby galaxies down here, only a few of those are moving towards us. Every other galaxy is moving away from us. And that alone is strange. If galaxies were moving around randomly, then some of them would be moving towards us, roughly half, and half would be moving away, right? And also in other directions. But the component of their speed towards or away from us, half of them it would be towards and half of them it would be away. But instead, all of these distant galaxies are moving away. None of them are moving towards. So something strange is going on. By the way, we now know what causes the scatter, why it isn't a perfect line. And there's two things. One is just experimental error. so not being able to measure things perfectly. And the other is that galaxies don't uniformly move like that. They move in all directions, but the further away you go, the clearer this tendency gets. And if you average over lots of them, you find a very nice line like this. So it's as though the universe is running away from us. Right? That's a very strange thing. Or you might, if you think about it a little bit, come up with another explanation. So suppose there was a big explosion at some point in the past in outer space. Forget about gravity and so on, but just an explosion that throws out a bunch of particles or galaxies in all directions at different speeds. If that were to happen, the more distant something is, the faster it's moving away from us, because that's how it got that distant. Right? So there was this event, this explosion, and the things that were moving fast, they went further because they're moving fast. And the things that were moving slowly, they didn't go very far. So when you look around now, the further away something is, the faster it's moving away from you. And the closer something is, the slower. So that's very reasonable. Except for one thing. Why would we be at the center? So this is almost going back to the Ptolemaic system in astronomy, where the Earth was the center of the universe. Why would we be at a special place? So this is just to show you an explosion. So these things that are moving, that are far out, they're moving very fast. That's how they got far out. Things near the middle are moving much more slowly. But why would we be at the middle? OK, well, let's come back to this balloon. So this surface of this balloon has a really interesting characteristic. There is no center to the surface. Right? If the balloon has a center, it's inside the balloon. But you're not allowed to think about that. You're a flatlander. You're in 2 dimensions. You just live on the surface. The surface has no center. No edge, nothing. There's no point on the surface that's much different from any other point. And not only that, wherever you are on this balloon, you'll see nearby galaxies moving away from you slowly, and further away galaxies moving away from you more quickly as the balloon grows. So everybody will see the same thing. Everybody will see an expansion, which makes it look like they're at the center, even though they're not, because every point is the same as every other point. Another thing that this analogy helps to illustrate is that this constant h doesn't really have to be constant. It can change with time. It depends on how fast the balloon is expanding. And it doesn't have to expand at the same rate for all time. Now, one very important thing to realize about expansion of space, it doesn't mean everything is expanding. You are not expanding. The Earth is not expanding. The solar system is not expanding. Even our Milky Way galaxy is not expanding. That's because you and all these other things I mentioned are bound together by forces that are much stronger than this overall tendency. So it just doesn't affect them at all. The only things that are expanding are distant galaxies or clusters of galaxies, so very, very large things, not smaller scale objects. So you can put that into the analogy if you want. You can imagine, instead of drawing these galaxies on the balloon, you can glue pennies or something to it and then blow it up. And then the pennies move apart from each other, but the pennies themselves obviously don't change size. So the pennies are galaxies, and OK, the space between them is the balloon. So that helps the analogy a little bit. Right. A big flaw in this analogy is that somebody's blowing up the balloon. And if they stopped, it stops growing. The universe isn't like that. It's more like, as I'll mention in a moment, an object with momentum, with inertia. So you give it a puff of air, and then it just grows, and it keeps growing. Maybe it slows down. Maybe it eventually turns around. But you don't have to keep blowing to keep it growing. It doesn't have a tension the way a balloon does that makes it want to shrink. OK, biggest problem with this analogy, it was in too few dimensions. So good luck, but you have to add a dimension to all of this. There's one analogy people sometimes make, which is a loaf of bread with raisins. Those are the pennies. So the loaf expands, and the raisins are the galaxies. They move apart as the loaf expands. But that's also bad, because a loaf of bread has a crust. There's an edge to the universe. We don't think there's an edge to our universe. So you really need to imagine something that's like the surface of a sphere, but in one more dimension. And this is called a hypersphere sometimes, or a three-sphere. It has the characteristic that if you go in any one direction, you'll eventually come back to where you started. If you could see all the way around, you'd see the back of your head. You can imagine that. But it's in 3 dimensions. Okay, so I'm not going to say much more about it. It's not easy to picture. But there is such a thing. At least it exists as a mathematical object. And that's one of the possible geometries for our universe. And this three-dimensional sphere, it can grow, just like the two-dimensional sphere does. All right. So let's talk a little bit about the fate of the universe. So now that we know that Hubble's observations are explained by the expansion of the universe, we can ask what's going to happen in the far future. What's the fate of our universe? And there's this famous line from Robert Frost that the world may end in fire or it may end in ice. And this nicely encapsulates the possibilities. So roughly speaking, there are three options. So one is that the universe is going to keep expanding forever. It may slow down in its expansion or not, but it will keep expanding forever. Another possibility is that it will reach a maximum size, a maximum extent, and then it will start to collapse. And the third possibility is sort of right in between these two. There's a close analogy, which works even at the level of the equations. If you throw a rock up, straight up off the surface of the Earth, or fire a bullet, so you give it an impulse so that it's moving up, and then no more force is acting on it, and forget about air resistance, then there's three possibilities. Well, if you really throw a rock up in the air, obviously it's going to fall back down. But if you were Superman or you lived on an asteroid with very weak gravity, then you could throw a rock hard enough so that it would not come back down. It would escape from the gravitational pull of the thing you're on, and if it doesn't encounter anything else, travel forever. The whole time it'll be slowing down, but it'll never come to stop. It'll never come to rest and return. So there's a critical speed you have to throw it to make that happen. It's called escape velocity. So if you throw something faster than escape velocity, it escapes. Slower than escape velocity, it falls back. Right at escape velocity, it sort of stops infinitely far away. That's the case that's right in between. So the universe is just like that. There's three possibilities. It can expand forever, it can recollapse, or it could be right in between. And because Einstein's theory relates geometry to gravity, it actually predicts three different geometries for these three different cases. The spherical case is the closed case where the universe recollapses. There's a thing called an open universe. It's like a negatively curved sphere. It looks sort of like a saddle. That's the case that expands forever. And in between is a space that actually has a flat three-dimensional spatial geometry without curvature. If the universe expands forever, then eventually stars will run out of fuel. Stars burn, sort of. They undergo a kind of fusion reaction. But eventually they'll run out of fuel for that reaction, and they'll go out. After a while, there'll be no stars left. The night sky will get darker and darker. Everything will get colder and colder. And that's the end. So that's called heat death. Very cheerful. And if you lived in this world for long enough, you wouldn't see anything in the night sky. Planets would get very cold because there'd be no suns to warm them up. Okay, so that's the ending in ice option. If the universe recollapses, then, well, it depends on how long this takes for this to happen. But let's say it happens maybe before all the stars have burned out. Then these stars in these galaxies will actually come back together. They'll get closer and closer together. They'll start smashing into each other. The universe will heat up. It'll get hotter and hotter. After a while, it'll be full of plasma. It'll be like the inside of the sun everywhere. And nothing can stop that. So one of the things Hawking proved is that once this starts to happen, you cannot stop it. In fact, it goes faster and faster because gravity gets stronger and stronger, pulls everything together. And after a certain finite amount of time, the density and the temperature and everything else will reach infinity. This is called a big crunch. And it's an example of a singularity. It's a point where Einstein's equations break down. By the way, in our universe, it seems that it will expand forever, as far as we can tell, in case you're wondering. It'll end in ice. All right. So the plan is that at some point, yeah, not yet. Well, yeah, at some point we'll take a break. There's some food and refreshments upstairs. And this seems like a good stopping point. So why don't we take a break now? There's food and refreshments upstairs. And Polly will sort of usher everybody back when we're going to restart. And we'll have a question and answer session. And then we'll continue with the lecture. All right? And then there'll be one more brief break later on. OK. So we're going to resume, and we'll start with a Q&A. So if you have questions, please raise your hands, and a mic will come to you. And just wait until the mic comes. Okay.
What I'd like to know is the whole universe laid out, and we're just encountering it as we pass through time? Is it already there, or is it developing at the present moment?
Yeah, that's a good question. So I think you're asking, is everything predetermined? Maybe is there?
Not exactly. Okay. Not exactly. But
Okay.
we're just traveling through time, encountering what's there.
So the question of why we feel like we're traveling through time, why we have that sensation, is a very tricky one. It's not something that physicists understand very well, I would say. I am going to come to the arrow of time, which is a closely related thing, just after black holes. So let's hold that thought, and if I haven't answered it, we'll have another Q&A session at the end that'll be longer, so we can come back to it. I think you were next.
Yeah, you mentioned that galaxies aren't part of the expansion of the universe, but isn't it true that they expand a little bit, but because they're so small with respect to the rest of the universe, they don't really expand that much? And plus the gravity that's in the galaxy?
Right. I guess it's true that if you took the same galaxy and you put it in a universe that wasn't expanding, it would be just a little bit smaller.
Okay.
So yeah,
But
there's a little bit of a stretching.
It would be hard to measure,
It
perhaps.
would be hard to measure.
Okay.
Right.
Thank you.
I've seen Interstellar 4 times.
Good.
Trying to calculate the mystery of that universe. I was intrigued to hear you say that gravity has a relationship with time. So does that mean in microgravity we age very quickly? So so our astronaut corps, they're going faster, and time is slowing down, but they're in microgravity. And what's happening with that side of things?
Right, it's a good question. Yeah, so in zero gravity, there's a certain rate of aging, which is faster than it would be if you're in a gravitational field, but it's not sort of infinitely faster. So in other words, someone in interstellar space in basically zero gravity will age a little faster than someone on Earth, but not that much faster. It's actually a pretty small effect. You really have to get very deep down into a gravitational field, like in Interstellar when they go close to the black hole because they land on this moon that's orbiting it, before it becomes noticeable. So it's not that there'd be a problem with someone that's in very, very weak gravity situation. They wouldn't age much faster than anyone on Earth.
And now that we've actually been detecting gravitational waves, how does those observations affect the theoretical people?
Well, they're very interesting. I'll come to them in just a moment. But yeah, that's a very exciting development. It's like opening up a whole new window into the universe. Yeah, it was predicted, so it's not a big shock, but it's like being able to hear all of a sudden, when before all you could do was see.
When you said that we're not expanding because atoms and molecules are bound together, forces much stronger than gravity, what forces are much stronger? What are they?
That's a good question. Actually, it's funny, all forces are much stronger than gravity. Gravity is by far the weakest of all forces. So there are 3 other forces in nature that we know of. The one that's most important for binding us together it's called the electromagnetic force. And that's what binds atoms into molecules. Inside atoms, there's a force that binds the nuclei together, and the quarks inside the protons and neutrons. That's called the strong force. And there's a third force called the weak force, which is not very important for much of anything. It's important for radioactive decays and so forth. But it turns out that all of those forces are much stronger than gravity. So the simplest example of this, imagine you have a refrigerator magnet. So you have a tiny little magnet. And with that magnet, you can lift a paperclip, let's say. So the paperclip is being pulled on by the entire gravity of the Earth, right? You have this massive, incredibly heavy object pulling as hard as it can with gravity on the paperclip, and this tiny magnet is stronger. So this shows you that magnetism, which is part of the electromagnetic force, is a lot stronger than gravity in the sense that a much, much smaller object can exert an equal or greater force than the entire Earth. Yeah. Is there? No.
Thank you. Given the tools that Hubble had at the time, how was he able to determine that galaxies further away were moving faster away than those close?
Yeah, that's another great question. So he had to measure two things. He had to measure distance, and he had to measure recession velocity. It turns out that the second one is actually the easier one, and the recession velocity. And the reason is that, you know when a car goes by you, honking its horn, it goes, "Meow." So when it's coming towards you, the sound is shifted up in pitch, and when it's moving away from you, it's shifted down in pitch, which is just because when it's coming towards you, the sound waves are kind of piling up on each other, and when it's moving away, they're getting stretched out. So that same effect, that's called Doppler shift, that same effect applies to light. So if an object is moving towards you, the light it emits will be a little bit bluer, and if it's moving away, it'll be a little redder. You don't notice this because it's a small effect for your eye to see, but it's easy to detect, and especially for a distant galaxy that's moving very rapidly away. So the way he measured recession velocity is by looking at the light from those galaxies and measuring how redshifted, it's called redshifted, how redshifted it was. And from there, he could get this recession velocity. But the distance is actually really hard to measure, and that was where he struggled. And in fact, he was off by a very large factor. He was off by about a factor of 10. Distance is hard to measure because, well, if you imagine you're in a big black empty space and there's a light bulb, and you want to know how far away it is, and with no points of reference, it's tough. If you know how bright the light bulb is intrinsically, like it's 60 watts, it's an old incandescent bulb at 60 watts, you could figure out how far away it is by how bright it seems to be, right? The further away, the dimmer it'll look. But you don't really have a good 60-watt light bulb in the universe. In other words, you don't have an object where you know exactly how bright it is, or at least Hubble didn't. So he had to use something called Cepheid variable stars, which are stars that pulse. And there's a relationship between their brightness and the frequency of this pulsation. But it wasn't a very good measurement, and he was pretty far off. And now we have various ways of doing it, but none of them they're all much better than what Hubble had, but still, that's one of the weakest points. The best thing is called a type 1a supernova, it's called a standard candle. It is a bit like a 60-watt light bulb. But even that is not perfect. So yeah, it's very hard to measure distance.
Have we been able to measure yet for sure whether antimatter falls in a gravitational field? And a second question, where do you think the missing antimatter is?
Okay, so antimatter is similar to matter, but with opposite charge. And if it encounters matter, it can annihilate and turn into energy. According to Einstein and according to every modern theory in physics, it will fall. It will behave exactly like ordinary matter. Gravity is totally universal, and the thing it acts on is the energy of something. And any matter certainly has positive energy. For example, you can annihilate an anti-electron with an electron, and you produce usually light, but with twice the energy of one electron. So it has exactly the same energy as ordinary matter. So if it didn't fall, or if it went up or something, it would violate everything we think we know about gravity. With that said, I'm not sure whether there's a direct test of that, because to make antimatter generally requires a really high energy event, like smashing particles together, and gravity just doesn't have much effect in those situations. As for where the missing antimatter is, it could be that there's just more matter than antimatter. So the question is essentially, there seems to be a symmetry between matter and antimatter, and yet we live in a universe that's full of matter and has very little antimatter. So where's all the antimatter? One possibility is that symmetry between matter and antimatter is actually broken in the early universe, so that you just produce a lot more matter than antimatter. Another possibility is that where we live, there's a lot of matter. Somewhere very far away, there might be a lot of antimatter. But there's not a very good understanding of that. It's one of the open questions. Why don't we take one more question, and then we can move on.
Hi, thanks. You said there's no edge to the universe. I saw a picture, they used a balloon and said it's like that, so you just go around or something. But
Yeah, as far as we know, I mean, of course, well, maybe it's not of course, maybe it's not obvious, but there's a certain distance that we can see in the universe. It's like a horizon. So if you're on an island in the middle of an ocean, there's a horizon, and you really can't see beyond that. There's something like that in cosmology. It arises because light travels at a finite speed. So you know when there's a fireworks display, you hear the sound after you see the light. But even the light takes some time to arrive at your eye. That means if you look at something distant, you're seeing it as it was in the past when it emitted the light. If you look further and further away, you're seeing further and further back into the past. And if you go far enough back into the past, the universe becomes opaque. So now it's pretty transparent. If you beam a laser in outer space, it'll keep going for a really long distance before it runs into anything, because space is empty. Back then, it wasn't empty. It was full of plasma. And in fact, it was like a solid, or like the inside of the sun. If you beam a laser pointer at the sun, it doesn't come out the other side. So the universe was like that far enough back in time. So you can't see further away than the distance that corresponds to that amount of time going back in time, which is about 13 billion years. So you can see pretty far, but that's it. OK, so if there's an edge and it's further away than that, it would be hard to tell. So we don't know for sure. But there's no reason for there to be an edge. There's no evidence for it to be there. And it's perfectly mathematically consistent, according to Einstein anyway, to have universes that have no edge and no center, just like the surface of that balloon. OK, well, thanks for the questions. Those were great. So like I said, there's going to be, at the very end of the program, roughly between 4:30 and 5, another Q&A session. So if you think of more questions, save them for then. OK, so I want to tell you about black holes. And then about Hawking radiation, Hawking's prediction that black holes are not exactly black. But before I can tell you about that, we have to understand what a black hole is in the first place. All right, well, as I was just saying, light moves at a finite speed. It doesn't move infinitely fast. It moves in American units at this speed, 186,000 miles per second. And according to Einstein, nothing can go faster than light. There's a kind of universal speed limit, which is the speed of light. By the way, the speed of gravity waves is the same as the speed of light. And it's not really that there's something special about light. Any kind of radiation, it all moves at this same speed. Now, sound, just to give you I'm going to make an analogy here for sound. So sound in water, it's a bit faster than sound in air, but much slower than light. It's like 5,000 feet per second. OK, so now imagine you have a river. And let's say there's a waterfall somewhere. And the river can be very straight and with the same depth until it gets to the waterfall. And as it approaches the waterfall, the current is getting stronger and stronger. And the water is flowing faster and faster. And so at some point close to these falls, the water is moving very fast. And now this is totally unrealistic. But let's imagine that close to the falls, the water is moving faster than the speed of sound in water. Okay? You can't actually have a river like this, nowhere close. But there are, in fact, experiments sort of like this, where you have a fluid, and you can make the fluid itself move faster than the speed of sound in that fluid. And people are trying to do these experiments. OK, so here you go. So if there's a place in this river where the current is moving faster than sound, that's this red line. In Washington, DC, you know a lot about red lines. So here's a red line across this river. And so closer, across this red line, closer to the falls, the water is moving faster than the speed of sound in water. So what does that mean? It means if you emit a sound over here, it'll actually get carried with the water. So you can emit it trying to have it go up the stream, but because the stream itself is moving faster than the sound, it'll get carried over the falls. OK? Now imagine that you're living in this river, and you're living upstream up there, and you're trying to investigate what's going on over here. You know there's something going on because whenever you send something that way, it doesn't come back, and you can't hear anything from over here. And if you send a friend over there, they never come back. So here you have some fish, and they're thinking hard about what happens. What happens if you cross this red line? So. OK, well, we know what happens because we can see. So I don't know what sound fish make, if anything. Let's say they squeak. I don't know. So if there's a fish in the river squeaking, and she's getting closer and closer to this line, then because the river's going faster and faster relative to the speed of sound, the sound she's making will take a longer and longer time to move upstream. And a sound emitted right on that line will kind of hover there. Right? It'll be moving upstream, and the water will be going the other way, and it'll just stay stationary relative to the bank. And a sound emitted past that line will never cross back over it. It'll go over the false. OK, so that's the idea of a horizon, this kind of horizon. So this would be a sound horizon. It's a line, or it's actually a surface sort of through the water, beyond which no sound can go back upstream. OK, so that's like a sound horizon. Now imagine that you have a very, very massive object, or a very dense object, so an object that has an extremely strong gravitational field. It's possible, according to Einstein, for the gravitational field to be so strong, or for the space to be so curved near that object, that not even light can escape. It's a bit like saying that the free fall velocity of things falling into this, which is like something being carried along with the current in the river, exceeds the speed of light close enough to this object. And you may say, you just told us nothing can move faster than light. That's right. And if you do an experiment locally, so if you're in a lab that falls into this thing, you won't actually notice much that's unusual. But if you try to shine something out of it, it won't make it. So not even light will get out, just like in the river. So there's this certain special radius around this very dense object, where if you're inside that radius, a light signal, and it doesn't have to be light. It could be a radio wave. It could be microwaves. It could be gravitational waves. But no form of radiation can escape. And if no form of radiation can escape, nothing can escape, because nothing can move faster than light or any other kind of radiation. All right, so it's called an event horizon because an event that takes place past it or inside of it will no information will come out. There will be no information about that event. It's hidden behind this event horizon. OK. So so imagine you have an object like that. It's so dense that it's surrounded by this spherical or roughly spherical event horizon. So nothing inside it can emit any light that you're going to see. So how are you going to see this object? Is it totally black? Well, the answer is it's not necessarily totally black in the sense that something which is falling in but hasn't yet crossed the event horizon may be emitting light. So this is like our physicist who's moving towards this red line and squeaking or whatever. And those squeaks are escaping upstream until right when the fish crosses that line. So stuff that's falling into the black hole before it crosses the horizon can emit light that you can see. And actually what it looks like is kind of interesting. It gets dimmer and dimmer as it approaches, and redder because there's a Doppler shift that affects it. So the squeaks of this fish would get fainter and fainter and pitched down more and more, approaching that line. For a black hole, the object falling in, emitting light, gets darker and darker and redder, and eventually it just disappears, and you don't see it anymore. So that's what happens to stuff falling in. But if there's a stream of stuff falling in, all of it emitting light as it goes, or some kind of radiation as it goes, you may see that. Right, so as I said, no information can escape from the interior because light can't escape, and so nothing can escape. So it's an event horizon. Now, according to Einstein, all of this is according to Einstein, inside this black hole, there's a singularity. Actually, I should say, it's according to Einstein's equations, but Einstein had trouble accepting the existence of black holes. He didn't really believe in them. Like I said, they're very hard to solve. And so although people very early on discovered black hole solutions in Einstein's equations, it wasn't understood what they meant or what they were for quite a while. And I'm not sure what Einstein thought at the end of his life, but at least for a while, he didn't believe that they made sense. So it's not really according to Einstein. It's according to Einstein's theory that there are these black holes. And there's this singularity at the center. So when we were talking about the big crunch, where the universe ends in fire, when it collapses on itself, there's something like that inside a black hole. There's a place where the density is infinite. And it's not exactly a place. A place is something you can avoid. You can't avoid the singularity at the center of a black hole any more than you can avoid the big crunch singularity in a universe that recollapses. Once you've crossed the event horizon, you're going to hit the singularity. There's no way to avoid it. It's not really a place. It's more like a time. It's a time where everything becomes infinitely dense. Now, normally when you're falling in a gravitational field, you don't really notice it. So astronauts orbiting the Earth, for them, they could be in the middle of empty space, and they would feel exactly the same thing. They're in free fall. The space station or space shuttle or rocket or whatever is in free fall around the Earth, which carries it in this circular path. So astronauts on the space station float around just like they would if there were no gravity at all. They're in free fall. However, if the gravitational field is strong enough, it'll have a different strength here than it does here. And so you can't really be in free fall and remain the same shape as you are. In other words, if this part of you wants to fall faster than this part of you, you'll feel a tugging. This is actually like a tidal force. It's what causes tides on Earth. So close to the center of a black hole, near the singularity, those tidal forces get extremely strong, and they tear everything apart. And it's called spaghettification. So here's an artist's conception. So don't fall into a black hole. OK, so what's a black hole? According to Einstein, it's a completely universal phenomenon. Anytime energy or matter is concentrated enough, so anytime the density is large enough, an event horizon will form. And again, Hawking contributed in a very significant way to this by proving that an event horizon must form and a black hole must form and there must be a singularity using Einstein's equations under certain circumstances where things are already collapsing. So it looks sort of like a black ball of some size out there in space. The size does depend on the mass of the black hole. So a black hole has a certain mass. It's however much mass fell into it to form it. And it can actually have a spin. So if it forms from a rotating cloud of dust, for instance, which is pretty typical, then it will have a spin. It's still black, but what it does is actually pull the space around it in a kind of swirl. So if you fall near it, you'll get pulled around, and you'll end up orbiting in that way before you fall in. So it does that. It's a little bit like water draining into a drain in a bathtub. And in principle, it could have electric charge. If you somehow threw a lot of electric charge in there, the black hole could have an electric field. But that's it. According to Einstein, black holes have mass, spin, and they can have charge. And those are their only characteristics. Otherwise, they're completely black and totally inert, apart from whatever might be falling into them. Now, in our universe, there are, as we now know, many black holes. And this is something that has become more and more clear in recent years, and it's now confirmed beyond any doubt. There are many black holes in our universe. It seems that most galaxies have large black holes at their centers, very large black holes, masses of millions, or sometimes even tens or hundreds of millions of suns. So it's like that black hole has a mass that's as much as 100 million, or 10 million, or a million times the mass of our sun. So there seems to be a so-called supermassive black hole like that at the center of nearly every galaxy. There are also much smaller black holes, and I'll come back to that in a moment. Now, in many of these cases, and in particular for the black holes at the centers of galaxies, there is what's called an accretion disk of matter. So the center of the galaxy is a very busy place. There's lots of stuff in there. It's pretty dense. And so that stuff is falling into this black hole. As it falls in, it forms a flat disk, sort of like the solar system. But it gets pulled into the black hole. And as it does that, it heats up and it glows, so you can detect it. I'll show you an artist's conception of that in a moment. There can be other black holes which are just floating around in empty space, and those would be very hard to detect. Not totally impossible, but very hard. One way to detect them, they're not emitting any light, there's nothing falling into them, but they have an effect which is sort of like a lens on the stars behind them. So if you have a field of very distant stars, and you have a black hole that floats in between you and those stars, you'll see this strange kind of warping, rippling thing going on with the field of stars behind it. That's called gravitational lensing. And that's because the gravity of the black hole is affecting the light, which is coming from those distant stars, and causing it to travel in curved paths. OK, so this is a conception of an accretion disk. This is not a black hole at the center of a galaxy necessarily. It's a black hole in orbit around a large star. And what's happening here is that material from the star is being pulled into the black hole. So the star is accreting onto the black hole. And this is a fairly typical situation. We believe that there are binary systems, so two objects. One of them is a star and one is a black hole. And when the black hole gets close enough, it starts sort of tearing away at the star and pulling material into it. And this often produces an energetic jet, which shoots up in the plane that's in the direction that's perpendicular to the accretion disk. And when that jet happens to pass across the Earth, you can see it. So this is to illustrate this other effect of gravitational lensing. So here's a black hole that's not pulling anything in, so it's really black, but there's a dense field of stars behind it. You can see that while this field of stars doesn't look very uniform, there's a kind of ring around here. So where's this ring coming from? Well, since we have this nice whiteboard, maybe I can draw a picture of it. So if you have a black hole here, here's the black hole, and you have a star here, and everything's in a line. You're over here, here's your eyeball, observing this thing. So light that's coming directly from the star towards you just falls into the black hole and you don't see it. Okay, so that doesn't come back out. But light that started off going this direction will actually get bent around like that, and light coming this direction will get bent around like that. And so what you'll end up seeing, it's as if there was some object over here and some object over here, and this is happening in all directions. So you see this ring. It looks like there's a ring in place of that star. Now, this only happens when the star is directly behind the black hole from your point of view. So it's kind of, it doesn't happen all the time. It requires them to be lined up. But in this image, which is just it's not a real image, it's a computer simulation of some sort. But you can see that there's this ring. It's called an Einstein ring, and it's coming from that effect. And there are real images like that where you see, it's called strong lensing. You see this, this effect. Okay, so you can detect a black hole even if it's not emitting any light, and even if it's not pulling anything into it, by this lensing technique, looking for this lensing. The other way you can detect black holes, and this is something which very recently has been in the news, so you may have heard about it, is that I mentioned that Einstein's theory predicts the existence of gravity waves, these ripples in space-time. And any motion of matter or energy produces gravity waves. But because gravity is such a weak force, as we were just discussing, the amount of energy that goes into those waves and the effect those waves have on any kind of detector, it's very, very weak. So to have any chance of detecting these gravity waves, you need an extremely sensitive detector. And it was only in the last decade that such detectors were produced and came to be. So the only detectors in existence are part of an experiment called LIGO, which stands for Laser Interferometer Gravitational Observatory, or something like that. So this is an aerial view of one of the facilities of LIGO. And what these lines are kind of long shed. Inside this shed, there's a tube, which has a vacuum inside. There's two of these arms at 90 degrees. Inside this vacuum tube, there's a laser beam going down the middle of it. And at the end here, which I maybe cut off a little bit in the picture, but at the end, there's a mirror. So this is an image of this mirror. There's a mirror hanging over there, which the laser beam is bouncing off of and then coming back. And what you do is you send laser this way, you send laser light this way. These arms have the same length. And if nothing is happening, the light will come back and you can interfere these two beams of light with each other. And you'll produce a pattern that looks sort of like ripples on a pond or something. It's like a fringy sort of pattern. And why is this interesting? Well, imagine you change the length of one of these arms a little bit. Then this pattern shifts, and you see it evolve and change. So if something changes the length of one of these arms, or makes this mirror move, this mirror is suspended from, essentially it's hanging from a string, but it's a very fancy string that has lots of vibration absorption. But if something makes this mirror rock back and forth, that changes the length of that arm, and you'll see that in this pattern. So basically, it's a way of measuring the difference between two distances, which are the two lengths of these arms, very precisely. So when two black holes merge, they orbit each other. They emit gravitational waves. That's a form of energy going out from them. And the emission of that energy causes them to fall together a little bit. So now they're orbiting a little closer and a little faster. They go faster, 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 faster. They finally merge. And at that moment, they emit a burst of gravitational waves that's very strong. And this instrument LIGO was designed to measure that. So when this burst of gravity waves arrives on Earth, it deforms the detector a little bit. It makes everything first get a little longer this way, then a little longer that way. So it makes everything kind of wobble, including the mirrors in LIGO. It's a very weak effect. You'll never feel it yourself. But LIGO is incredibly sensitive. and it can measure this tiny difference in this tiny deformation, if you want, so a tiny change in length, relative length of these two arms. Now, it's so sensitive that it can detect trucks driving by, waves hitting the beach. People that work there are instructed not to run because in the control room or anywhere near it, because their footfalls can be measured. So if they get excited about something, they can't run across the control room to tell anybody. And there's actually two, well now there's more than two, now there's several, but originally there were two of these facilities. One is in Louisiana, not far from the ocean, or not from the Gulf of Mexico, and waves were a problem there. The other one was in Washington State, and logging trucks were a problem there. But the way that this experiment works is that they would only look at an event if both detectors detected it. And not at exactly the same time, but almost exactly the same time, the difference being the time it takes for the gravity wave to propagate from one to the other. Because most of the time, it's not hitting them at the same time. It takes a tiny fraction of a second, but gravity waves move at the speed of light, so they don't hit them both at the same time. So if a logging truck drives by one, it's very unlikely that an almost identical signal will be measured at the other one at exactly or almost exactly that same time. So this is a powerful way of discriminating a real event, a gravity wave, from something else. And this was the first event they detected. This is just noise here. This is the signal. It may not be very obvious looking at it that the signal is all that different from the noise. But the chances that this signal would occur at both of these detectors with just the right offset in time are less than 1 in a million. So they do a lot of statistics to measure that. And moreover, this signal is precisely what was predicted by Einstein's theory. Actually, I told you guys a while ago that this problem of just two objects orbiting each other can't be solved exactly and wasn't even solved on a computer until about 15 years ago. The reason that was such an important problem was to predict what LIGO should see. And fortunately, it was solved in time. It was solved, like I said, about 15 years ago by Franz Pretorius. And so that allowed this prediction to be made that confirmed this. So that first detection was in September of 2015. The first number is the year, and this is the month. I think this means on the 14th. That's when it was detected. It was announced sometime later because they spent a long time making sure that it was a real event. In fact, this experiment is so careful with making sure that the events are real and significant and that they're not having false positive discoveries, that they would even inject fake data, like events that aren't real, in such a way that nobody working in the experiment would know if it was real or not, except for the 3 leaders of it. And then they would allow the collaboration to get excited and prepare a paper and have everything ready, and then they would reveal that it was fake, just to test this whole stream of how it worked and to make sure that people didn't sort of become biased by thinking that this had been a real event. If the 3 leaders of the collaboration had died in a plane crash or something, I'm not sure what would have happened. But in any case, they're really very, very careful about all this. So everything is done blind. They don't know what's real and what's not. Everything is automated. Nobody is picking and choosing events. And since that date, they've detected now, 6 of these mergers. This one wasn't quite significant. That's why it's dashed. But the rest are all significant detections. And what does this vertical axis mean? Well, these are the 2 black holes that merged with each other. This one had a mass of about 35 suns, and this one had a mass of about 30 times the sun. And what they produced is a black hole with a mass of about 60 times the sun, which, if you look carefully, you'll see is not the sum of these 2. It's not the addition of these 2. It's a little less. And that's because a lot of energy was radiated away in gravity waves, and that's what was detected. So several suns worth of energy equivalent was radiated away in gravity waves. And that's an incredible, it's an enormous amount of energy. And these are other detections. So these all involve black holes that are several times the mass of the sun, up to maybe 30 times the mass. And it's actually an interesting question where these come from. It wasn't expected that there would be black holes in this mass range. But now they've been seen. OK, so that's what black holes are, according to Einstein, or at least according to Einstein's theory. They've now been detected in a variety of ways. I think they're definitely out there. And again, according to Einstein, nothing can escape from these things, because once you fall in, you're trapped behind this event horizon. You can't get any information or any kind of message out. Or at least that's what was believed until Hawking came along. What Hawking realized is that when you combine quantum mechanics with Einstein's theory of gravity, things that would have been impossible are no longer quite impossible. So a good example of this that's closely related to Hawking radiation is a phenomenon called quantum tunneling. So quantum tunneling is the following physics. Imagine you have a rock or something which is trapped in a valley, or trapped in the bottom of some sort of, not just a valley, but like a lake bed. So it's really down in some kind of minimum. That rock is prevented from escaping from that lake bed and getting out into the countryside beyond, because there's some mountain surrounding it on all sides, right? So it has to climb up to the top of this mountain and get back down again to escape. And if it's just a rock sitting there, it has no way of doing that. Now, obviously, somebody could pick it up or push it and get it to the top, and then it could escape. So if you add energy to the system, the rock can escape from this lake bed. But without adding energy, it can't get out. It's impossible. Now, a black hole is a little bit like that. So there's a barrier, which is the event horizon, through which nothing can get out, according to non-quantum classical physics. It's like having a barrier which is kind of infinitely high. You can't get out no matter how much energy you have and no matter how fast you're moving. But in this situation, there's a probability, according to quantum mechanics, that the rock will just find itself over here. And this is called quantum tunneling. It tunnels, in a sense, through the barrier, even though this would be impossible in classical physics, and even though nobody gave it any energy. It just happens. Now again, this is something which has been observed. In fact, of all the things I've told you about, quantum mechanics is by far the most established. Quantum mechanics is at the basis of every operation in your phone, for instance. So all of solid-state electronics relies crucially on quantum mechanics. It's at the basis of modern chemistry. It's used in all sorts of different technologies, nuclear power, nuclear weapons. All of this is based on quantum mechanics. It's a very well understood and very well established theory. And there's no question that quantum tunneling occurs. And there's something called a scanning tunneling microscope. Even some of the scans you can get in a hospital rely on this. So quantum tunneling is a real thing. It's a problem in transistors. If you shrink them down too small, electrons start hopping out of the wires, even though they wouldn't be able to classically because of quantum tunneling. So it's a real thing. Now, with that said, a black hole is an exotic object that we can't do experiments on. So I said a while ago that this prediction of Hawking is very plausible, but it's still not something that's been confirmed experimentally because we don't have black holes to do experiments on. But what Hawking predicted mathematically was that you have a black hole. According to Einstein, nothing can escape from it. There's a kind of barrier that prevents anything from getting out. But if you include quantum mechanics in your calculations, you discover that a particle or something, it doesn't have to be a particle, it can be some light or some radiation, can escape from the black hole and will escape from the black hole at a certain rate. In fact, it will escape at the right rate that it looks like the black hole is a warm, I don't want to say hot, because for it to be hot, it would have to be very small, but it's a kind of warm thermal object. So it emits radiation in a particular way that's characteristic of objects with a temperature. As it emits this radiation, it's losing energy, because it's emitting radiation to infinity. It's losing energy. Black holes with less energy, with less mass, are smaller. So the black hole gets smaller when it emits some radiation. And actually gets hotter when it gets smaller, according to Hawking. So now it emits more radiation, gets even smaller. After a while, it should just evaporate entirely. However, the time that this takes for a black hole that's the mass of the sun, for instance, is enormous. It's much longer than the age of the universe. And that's because a black hole that big is very, very cold. So it's really, really slow. So to see this happen, you actually would have to have a very tiny black hole with a mass that's much, much smaller than the mass of the sun. If you could make one in a lab, like I said, it would be dangerous, but you could see it happen. But it's hard to make black holes in the lab, because you have to produce something that's so dense that it forms a horizon. And that's, well, we don't have any way to do that, currently at least. But according to Hawking, this should happen. Black holes should evaporate. OK. So I won't say much more about that. The reason it's such an important discovery is that it creates a number of paradoxes. It's a very confusing result for a number of reasons. Well, if people want to hear more about that, you could ask questions in the Q&A session at the end. But let me turn now to the arrow of time. So this is a puzzle. This is something which goes back before even Einstein, back to the late 19th century, to Boltzmann. And let me start actually by, again, discussing Hawking radiation in a certain way. So let me give you an argument which would suggest to you that it's not surprising that black holes can evaporate. So here's the argument. So imagine you have, this is a kind of a thought experiment. Einstein loved to do these, right? You imagine some situation, maybe you can't do it really in the lab, but you can imagine it and you can ask, what would the laws of physics predict for it? So imagine you have a really, really, really big box. It's sealed, nothing can get in or out. It's a really giant box. And it's out there in the middle of empty space, so there's no gravity apart from whatever is created by the particles inside the box. And let's say you have a lot of particles inside the box, but it's so big that they're very diffuse. So they're not close together. There's no high density. And it's very unlikely, by the way, I mean, this is not a bad model for what the early universe is like. It's full of particles. It's pretty unlikely that those particles will form a black hole. And the reason is just that the box is so large that the typical density is very small. Particles are very far apart from each other. And each particle has only a tiny gravitational field. To form a black hole, they all have to clump together at one point very densely. Okay, so that's unlikely, very unlikely. But it could happen. There's nothing that forbids it from happening, except that it's just not very likely. And in fact, if you were to wait long enough, if you were just to sit there and twiddle your thumbs and watch this thing, eventually, just by random chance, the particles would find themselves close enough together that the density would be high enough that they would form a black hole. And remember, according to Einstein, once you form a black hole, that's it. Nothing can get out of it. So you have this black hole, and it has a certain mass, and that's it. So let's imagine that it happens, either by chance, or you arranged the motion of these particles so they're all going towards each other. So after a while, they all find themselves at the center or something. So let's imagine it does happen. Now, there's a really curious feature of the laws of physics, which is called time reversal invariance. And what it means is that the laws of physics that govern everything, the microscopic laws of physics that govern interactions between particles, the forces between them, and so forth, those laws look exactly the same if time is running forward towards the future as if time is running backwards towards the past. So to put this in concrete terms, imagine I made a video, a movie, of something happening, two particles bouncing off each other. Maybe think of two pool balls bouncing off each other. And now let's say I play that movie backwards, or I don't tell you if I'm playing it forwards or backwards. If all you see is this collision, you're not going to be able to tell whether time is running forward or time is running backward. And that's true for individual particles bouncing off each other. It's true for pool balls as long as I don't go long enough that you see them slow down from friction. But of course, it's not true for most of the events in the world. Like if you see somebody diving into a swimming pool and you see a big splash of water come up, and now I run that movie backwards, that's a person coming up out of the water feet first, a bunch of droplets of water converging, forming a perfectly smooth surface just as the person gets ejected from the water. It sounds impossible, right? But it's not. It doesn't violate any laws of physics, well, except one that we'll get to. But it doesn't violate this fundamental fact that the laws of physics are time reversal invariant. So coming back to the black hole, if something can happen one way in time, there is nothing that forbids it from happening the other way in time. However, it may be very unlikely to happen one way or the other. A person undiving out of a swimming pool is very unlikely. You've never seen it, and you never will, because it's fantastically unlikely that everything would be carefully prearranged to make it happen. But remember, I said that to make the black hole in the first place was actually the unlikely thing. It was hard to get those particles to all find themselves in the same place at the same time so that they're so dense that they form a black hole. So that was the thing that was unlikely. And if you have this symmetry in the laws of physics, it should be possible to go the other way, that the black hole turns into this gas of particles which are flying around. That's evaporation. Okay, so this is a kind of general argument that tells you that black holes must be able to evaporate if the laws of physics are going to be reversible. And we believe they are, at least once you put it in quantum mechanics. So, okay, so that's just an argument that says, well, maybe you shouldn't have been so surprised that there's Hawking radiation. and black holes can evaporate. But it brings up this other question that I mentioned. Why do things only seem to happen one way in time once you get away from pool balls bouncing off each other or particles interacting? Why doesn't anybody ever undive out of a swimming pool? Why was it so hard to put Humpty Dumpty back together again? You can break an egg. Good luck putting it back together. So where is that coming from? Why do we remember the past and have very little idea what's going to happen 5 minutes from now? And certainly 5 years from now, right? So why is that? The future and the past are very, very different. Why do we feel like we're progressing through time in the present? Well, the sort of quick answer to that, as far as we know, is the second law of thermodynamics, which says that entropy increases. Or more precisely, it says entropy does not decrease with time. Now, I just told you the laws of physics are the same going forward in time, going back in time. So to say entropy increases, well, that means it does something different going towards the future than going towards the past. Than going towards the past. Going towards the future, it would be increasing. That would mean going towards the past, it would be decreasing. So that's not time reversal invariant. So what am I talking about? Well, the laws that are time reversal invariant are the microscopic laws of physics, the laws that govern forces and interactions of particles and so forth. And we believe that the laws of thermodynamics, like the second law, are not fundamental laws at all. They're just consequences of these microscopic rules. Okay, so thermodynamics is the science of things like temperature, pressure, how the air is distributed in the room on average. And what we believe is that those principles that govern how the air is distributed in the room and what its temperature is and so on follow from these fundamental laws, but they're not fundamental in themselves. So the second law of thermodynamics, it should be something we can explain from the fundamental microphysical laws. And yet, those are time reversal invariant. Those are the same going forward and back. And the second law is not. So how can that happen? Well, okay. Suppose the entropy happens to be low now. It just happens to be. You just start that way. Then what do you expect is going to happen? Well, I should tell you a little bit about what entropy is. Entropy is essentially a measure of how many possible states there are consistent with whatever macroscopic properties the system has. For example, I might tell you how many molecules of air there are in this room and how much energy they have in total and how big the room is, and that's it. And then entropy is the number of possible configurations of the air molecules that's consistent with all that. So I'm not allowed to add and subtract air molecules because I told you how many there are. I'm not allowed to put them outside the room. They're in this volume. I'm not allowed to change the total energy, but I can give one molecule more energy than another. I can move this one over there. How many ways are there to do that? Well, obviously there's a lot because there's a huge number of air molecules in here. I could put them all up in that corner. I could put them up in that corner. I could spread them uniformly. I can change their energies relative to each other. So there's a huge number of states, of configurations, which are all consistent with how many there are, how much energy they have, and how big of a room they're in. And that number is the entropy. So what's a low entropy state? Well, a low entropy state would be insisting that all the air molecules are in that corner. Okay, hard to breathe, but let's say they're all in that corner. That's low entropy because there's very little volume up there. So there's a lot fewer states like that than there are where they could be anywhere. If I put all the air up there, what do you think is going to happen? It's immediately going to spread out and fill the room and become very uniform. And the reason that happens is just because there are many more ways for it to do that. It's a statistical thing, really. Now, another example. I have two little kids. I spend a lot of time trying to decrease the entropy locally, cleaning things up. If you clean up a toddler's room and then the toddler comes home, that's what happens very rapidly. And the reason is just that, well, kids and these microscopic laws of physics, they're not really random, but they're just doing whatever they want to do. And because there's so many more ways for it to look like this than there are for it to look like, whoops, next slide. Come on. This, right? This is a very special arrangement. There's not very many ways for it to look like that. There's really just one way. But when you start throwing your socks in all directions or just mixing them up, there's many, many more ways. So really, what we think is that the second law of thermodynamics, it's not that there's a fundamental asymmetry. It's not that time is different running forward and back. It's just that if, for whatever reason, you live in a universe with low entropy that's initially ordered, it will become less and less ordered. In other words, its entropy will increase. Okay? So the explanation for this second law of thermodynamics is just that the universe in the past was more ordered and had lower entropy than the universe does now. But this really begs the question. Let's say this first. So the entropy will continue to increase until, or unless, it reaches the state with the maximum possible entropy. And that, by the way, is called thermal equilibrium. When we talked about heat death, that's an example. Everything comes into equilibrium. You don't have hot stars and cold empty space and warm planets. Everything comes to the same temperature. You don't have variations in density or pressure or anything else. You don't have any motion of any sort in equilibrium. Equilibrium is incredibly boring. It's just everything is constant, nothing changes. There's no life. Nothing can happen there. That's the future if we can describe the universe as a thermodynamic system, because its entropy must increase until it reaches this maximum. That's what will happen to it. Now, as I said, we can understand this if we can understand this second law of thermodynamics, why the entropy is increasing, if the early universe had low entropy. And I believe, although it's hard to prove this, that explanation, as far as it goes, it suffices to explain why eggs are easy to break and hard to unbreak, why you remember the past and not the future. Everything that we think distinguishes future from past, I think it can all be explained if the early universe had low entropy. But there's still a question hanging in the air. Why was the entropy low in the early universe? Where did that come from? If there are many more states with high entropy, then why was the early universe in this very special state with low entropy? No one knows the answer to this. It's still one of the central mysteries of physics. But Stephen Hawking made an important contribution to this area of inquiry. So this is someone named Jim Hartle. He's a professor at the University of California in Santa Barbara and a longtime collaborator of Stephen Hawking's. Back in the 80s, the early 80s, Jim and Stephen proposed a mechanism for how the universe could be created from nothing via a kind of quantum fluctuation. So quantum mechanics allows a lot of things to happen. It allows for tunneling, and it's fundamentally random. So stuff happens in quantum mechanics without any obvious cause. One of the things that they posited could occur is that an entire universe could be produced randomly by a quantum fluctuation. And the reason this is possible at all is that it turns out that in general relativity, the total energy of a universe that has a kind of spherical shape is 0. Now, how could it possibly be 0? It's got stuff in it. Well, gravitational energy is inherently negative. If you think about, if I drop this, it's going to pick up kinetic energy. It's going to move faster and faster as it falls, right? So it's gaining energy, but energy is conserved. So there must be an increasing negative amount of energy as it goes down. And that's the gravitational potential energy, it's called in Newtonian physics. So in that sense, gravitational energy is negative. And it turns out then that a closed universe, a universe that doesn't have an edge, has exactly 0 energy. So things that have exactly 0 energy can be produced out of nothing because there's nothing to prevent them from being produced. Energy is conserved. You can't produce something with non-zero energy out of nothing, but you could produce a 0 energy universe out of nothing. And they were able to write down a mathematical solution for this, which can be represented like that. What it describes is a closed universe that appears and then starts to grow, starts to expand and become large. When it appears, it's very tiny, but it grows and it becomes very big. And according to this proposal, when the universe appears, it can have very low entropy. So that's what we wanted. We wanted to know why the early universe would have very low entropy. But this is certainly not a complete answer to this question for a number of reasons. First of all, we don't have a theory in which we can create a universe from nothing. There is no such theory. We don't have one. We don't know what it would look like. If universes can be created, they can probably be destroyed by whatever is the time reverse of that mechanism. We have theories where particles can be created and destroyed, not where universes can be. And so Hartle and Hawking, lacking such a theory, had to reason essentially by mathematical analogy. So it's better than verbal analogy, but it's still an analogy. It's not something you can really predict precisely. And even if we did have a universe in which, theory in which universes can be created and destroyed, if its laws were time reversal invariant, it couldn't explain this second law of thermodynamics. It couldn't explain why the early universe would have low entropy. It would be much more likely in such a theory for it to have higher entropy. So this idea doesn't really answer this question. But still, it's a piece, and it's a very interesting and important piece. It's one of the few ideas that might have a chance of explaining this. OK, so I just want to close with a quote. So I'll read you a quote from a book by Freeman Dyson, and then I'll play a quote from Stephen Hawking. So I'm reading this book by Dyson. Freeman Dyson is a very famous physicist. He never won the Nobel Prize, but he probably should have. He's still alive. He's 94 years old. And he's been at the Institute for Advanced Study in Princeton almost continuously since 1948. And he wrote a book recently. It's called Maker of Patterns, which is an autobiography by letters. So he wrote a letter to his parents in England every week for many decades. And I happened to be reading this book while I was preparing this talk, and I came across this letter. This is a quote from a letter in which he describes this visit by Stephen Hawking. So this is back in 1970 when Hawking was 28 or so. And just in case anyone has trouble reading it, I'll read it. I was taking care of Stephen Hawking, a young English astrophysicist who came here for a 6-day visit. Here means in Princeton. Stephen is a brilliant young man who is now dying in the advanced stages of a paralytic nerve disease. In the last few years, he has produced a succession of brilliant papers on general relativity. So this was before Hawking radiation. These are the papers on singularity theorems. In conversation, he is one of the quickest and most penetrating minds I have come across. He is confined to a wheelchair. These days, while Stephen was here, I was in a state of acute depression thinking about him, except for the hours when I was actually with him. As soon as you are with him, you cannot feel miserable. He radiates such a feeling of strength and good humor. I was running after him to escape my misery. So here again is Hawking in this zero-gravity airplane. And you can see he's having a pretty good time.
You know what year that was?
I'm not sure. I think maybe 10 years ago, but I'm not sure. Probably you can find it with Google. If you just Google images of him, it's everywhere. So I'm going to play a quote. This is from an end of a talk that he gave, a TED talk that he gave. I couldn't figure out how to embed it, so I have to go here. Hopefully the sound works.
I have sought to understand the universe and find answers to these questions. I have been very lucky that my disability has not been a serious handicap. Indeed, it has probably given me more time than most people to pursue the quest for knowledge. The ultimate goal is a complete theory of the universe, and we are making good progress. Thank you for listening.
So thank you for listening. We're going to take a break now for 10 minutes, and then we'll have a Q&A session for about half an hour. And we need to finish right around 5 o'clock. OK, so we'll have a Q&A session now. And again, please wait for the mic.
OK, I have a question. And then the person who was sitting next to me, who's not a physicist at all and was a little confused about it, asked me to ask you a question. She's sort of recovering upstairs.
OK.
Okay. My question is, of course, why is there something rather than nothing? And her question was, what does nothing look like? And she's a non-physicist, so.
There's a book by Lawrence Krauss called something very similar to that, Universe from Nothing, yeah. And I mean, what he's describing in that book is essentially this idea. I think the way he describes it is a little bit too strong. He makes it sound like we know the answer and this is settled, or in any case, there's a reasonable theory that really does this. Like I said, this idea is essentially reasoning by analogy, and the analogy is to the production of particles in vacuum or in the presence of something like an electric field, where you can produce an electron-positron pair out of nothing but the electric field. They can just spontaneously appear. To really have a theory of production of something from nothing, you need a theory of nothing. And what does that mean? So at least there have to be some laws of physics or some sort of mathematical equations. It's not clear that that's really nothing. And even then, like I said, we don't actually have a theory like that. We don't have a theory, even at the level of mathematical equations, that describes this production of universes from some sort of vacuum that doesn't have any universes in it. That doesn't really exist. So I think a lot of people suspect that it might exist. When you add quantum mechanics to Einstein's theory, Einstein's theory is a theory of space and time. Space and time are dynamical. They can expand, they can contract, there can be waves. And usually when you add quantum mechanics to a theory like that, there is a state which contains nothing. In the case of electromagnetic forces, it means that it contains no photons, no light, no electric fields. And there is such a state. It's called the vacuum state. So if we had a quantum theory of Einstein's theory of gravity, the vacuum state of that theory would be this thing we're discussing. It would be this nothing. But we don't actually have a quantum theory like that we understand. So yeah, we're a long way from knowing the answer. Did I answer both questions? Yes.
Specifically with regard to the shape here, why does it have what appears to be an inflection configuration rather than being strictly conical?
Mm-hmm. Yeah, so this is a little bit tricky to explain, but I'll try. What this is representing is two different shapes glued to each other. So this one is a hemisphere, and this one is half of a hyperboloid. And the inflection point you're talking about is right here, where you glue them together. The reason for doing that is that, again, in this analogy that essentially was being made here, so the closest analogy is if you have an electric field, and you can imagine a capacitor. That's two plates of metal, and one has positive charge and one has negative charge. In between is an electric field that points from one plate to the other. There's a quantum process where an electron, that's a particle with negative charge, and a positron, that's an anti-electron that has positive charge, can spontaneously appear in between. And then one flies to one plate, the other flies to the other plate, and partially cancels this charge that was there and reduces the field. And there's a mathematical description of that process which would look a lot like this. It would look like the edge of that. So there'd be an electron here, a positron here, and they then fly apart. So the vertical direction would be time, the horizontal direction would be position. And this motion is an accelerated motion where the electron or the positron is flying off under this field. This part of it is the quantum tunneling part. And the reason it has a different curvature, and therefore this inflection point, is because quantum tunneling is a strange process. It's not classical physics. It's sort of like an event that takes place in imaginary time. That's the best I can do. This is a technical question, and there's not a simple explanation, but that is the answer at some level.
You mentioned a black hole all by itself in space you couldn't see. And my question is, it relates that to dark energy and dark matter, and trying to figure out what dark energy, dark matter is. Mm-hmm. I'd like your viewpoint on why isn't all this dark energy, dark matter just a bunch of black holes we can't see?
Yeah, that's a great question. So first of all, dark energy and dark matter are different. And for anybody who doesn't know what they are, when we talked about this expansion of the universe, I was saying, okay, there's some initial impulse that makes it expand. That part we don't understand. But once it's expanding, it keeps expanding unless there's enough gravity in it to pull it and turn it back around. Right? But while it's growing, you would expect the expansion rate to slow down. because all the gravity in it, all the galaxies and so on, are pulling on each other and slowing down the expansion. Just like when you throw a rock up in the air, it might escape, but it'll slow down as it goes out. Instead, the universe is actually expanding faster and faster with time. Its expansion is accelerating. And whatever is responsible for that is what's called dark energy. All right, so that's dark energy. Dark matter cannot be the same thing if it's matter. Well, it really cannot be the same thing. Dark matter is some form of mass which is present, we think, in most galaxies, and which is not visible. It doesn't emit light. But the reason we think it's there is that you can determine how much mass there is in a galaxy by observing how it rotates, how things orbit around it. It's like if the sun was somehow black, but you could see the planets moving around in orbits, you would know there was a sun, there had to be an object there with the mass of the sun, because that's what's making the planets move in orbits. It's just like that. You see a galaxy and you see it rotating, you see the stars in it orbiting around its center, and you can figure out how much mass must be in it. And it's much more than the mass that's in gas or stars. So whatever that stuff is, we call dark matter. Now, could it be a bunch of black holes? Actually, maybe. Probably not, because of various constraints. So one of them is this lensing effect, that if dark matter were black holes, these black holes would sometimes just happen to drift in front of distant galaxies. There would then be a lensing effect. And people have searched for that and not seen it. Another reason is that in the earlier universe, those black holes would not have been in vacuum. They would have been surrounded by plasma, because the universe was full of plasma. They would have sucked it in, produced light from the accretion, and we don't see that either. So there are a number of constraints like this. None of them are totally solid, and if there's a range of masses of these black holes, it might be possible. It's certainly something people are thinking about very actively, actually, especially now that LIGO detected all of these mergers. Yeah.
Excuse me, I appreciate the clarity of the answers, particularly the last one. That was a good question. I'd like to go from your discussion of entropy to the inverse, which in Claude Shannon's presentation of information theory, that would be information. Mm-hmm. I'm familiar with that as a computer geek, but I don't understand the use of that term information with Stephen Hawking's work. I know this is a little bit outside of this, but why are you worried so much about information loss when we lose it so easily over a computer pipe?
Right. Yeah, so information in the context of information loss and Hawking's work is not quite in the sense of Shannon. It's more, let's call it a loss of predictivity. So even in quantum theories, if you could know exactly what the state is of everything, then you could evolve that state in time and determine precisely what the state is at a later time. So for example, if you know exactly what the quantum state is of two particles and you shoot them at each other, you can predict what the result will be, what the state will be at a later time with 100% confidence. Predicting the quantum state is different from knowing what you're going to measure when you measure it, but you can predict the state. And you can actually measure the state if you could do this experiment many times over and over again with the same initial conditions. So you can check your prediction. What Hawking was worried about when he discovered Hawking radiation is that it seems that since black holes have no characteristics other than mass, spin, and charge, they have no memory of the state that they formed out of. So for instance, if you formed a black hole out of encyclopedias or graduate students, you would get the same black hole as long as you had the same total mass. And then it would evaporate, according to Hawking, into thermal radiation, which wouldn't remember those encyclopedias or graduate students that it was formed out of. So yeah, so there didn't seem to be a way to preserve the information about the initial state, meaning that the quantum state didn't seem to evolve in a predictable way. So that's what he was worried about. I mean, it is related to Shannon entropy in the sense that in quantum mechanics, the analog of Shannon entropy is conserved. It doesn't change in time. But in this process, in this Hawking evaporation process, at least the way Hawking thought about it, it would change with time. It would violate a postulate of quantum mechanics. So, which is that the state is predictable. The state at later times is predictable. I think there was maybe a question here, though, that you've been waiting for a while. Yeah.
Thanks very much. Two questions. One, what happens in the infinite density of a black hole to atomic and subatomic particles? What do they become? And the second question is, if you could control the government's budget and if you had some truly brilliant graduate students, which of the sort of unknown, the sort of questions that are lingering in theoretical physics, what would you allocate that money to and your graduate students to? What are the really big priority questions?
Okay, so the first one's easier, so let me start with that. Yeah, so what happens to atomic and subatomic particles? There's a theory of atomic nuclei, which says they're made out of protons and neutrons, and there's a theory of protons and neutrons that says they're made out of quarks. Quarks are something that we're pretty sure exist. That you can smash together nuclei hard enough that the quarks sort of briefly show themselves and you can measure them. If you made a high enough density state, quarks would no longer be bound into nuclei. They would just all be crammed together in a different state. A little bit is known about that, but not a whole lot. It turns out, although there's a good theory of quarks, it's really hard to calculate with. It's sort of like Einstein's theory of general relativity. You need a powerful computer, and even with that, it's difficult. So we know a bit about that state, but not a lot. If you smash those together even more, as would happen inside a black hole, we don't know. There's probably some substructure to quarks. There's a theory called string theory, which is an idea for what might lie below that level. It might be right, it might not be. So we don't really know the answer. Past a certain point, it becomes just not quite anybody's guess, because there are a lot of constraints, but there's a lot of uncertainty. It's like an onion, right? You keep peeling away layers, but there's always more. So we can go down to some level in length scale, which is quarks. Below that, we're not sure. And when you squeeze everything together, you get all the way down. You get an infinite density state, it seems. Okay, as for what questions I would allocate money to, first of all, I think of science and scientists as like, I don't know, an anthill, in the sense that ants sort of swarm around and they look for food, right? And if they find food, they all swarm there, not all. Most of them go there and sort of eat it until it's gone. There's always a few wandering off in various directions, just in case they get lucky and find something. And you never know what you're going to find if you're an ant, right? You're crawling along on the ground, you can't see very far. And a lot of those ants that wander far find nothing. Maybe they fall into a river or something and die, right? I mean, you just never know. I think it's important to have both of these things going on. So there's some questions that are clearly important that you should put a lot of resources into. And at the same time, you shouldn't abandon these ants that are wandering off and asking big questions and taking a big risk. So you don't want to focus all your resources on the obvious things. And you also don't want to ignore them and put all your resources into high risk, high gain projects. And exactly where this balance lies, I'm not sure. But I think there's a structure that does a reasonably good job of identifying it. So there's structure of federal grants and so on. As for which of these problems I think is most important, well, I briefly mentioned cosmic inflation. So I think that's a very important question because we're pretty sure it happened. So this is a phase in the very early universe which was responsible for all of the stars and galaxies that we measure today. And there's pretty good evidence that it happened. But we don't know what the physics was that's responsible for it. This black hole information question, which arises out of Hawking radiation, that's been very fruitful, thinking about that. And it's far from well understood. So there's a theoretical research program there, which is really active and really interesting. And in fact, you mentioned Shannon entropy. It's connecting information theory to fundamental physics in a really interesting way. Let's see, what else? The story with black holes, detecting merging black holes, it's very, very exciting because all of a sudden there's a new way to observe the universe. If we build a few more LIGOs that are more sensitive, we're going to start seeing black hole mergers all over the universe. And it's like having a whole new kind of instrument to observe the universe with. It's a new kind of telescope in a sense. Yeah, I mean, pretty much everything that I mentioned is interesting. Some things are a little bit more, so that's a very active area. I don't know, singularity theorems in general relativity is not so active because it's pretty well understood at this point. So the stuff that Hawking did in the early 70s, late 60s. But yeah, the early universe, understanding the early universe better and understanding the current universe better through gravity waves, those are really exciting topics.
So, right, as you mentioned in your talk, there are two dominant theories, the quantum mechanics and the theory of general relativity. So quantum mechanics deals with very small things at the atomic level, like photons and the atom, the electron. And general relativity deals with everything on a large scale, the planets moving and so forth. But we are looking at the galaxy, and one of the tools that we're determining these ideas is, at least with the expansion of the universe, is the Doppler effect on light. But light is inherently a quantum mechanical thing. So how do astrophysicists square the fact that these two laws don't agree with each other, but they work very well at a small scale or a large scale, but suddenly we have astrophysicists applying quantum mechanics at the large scale, that is to explain large scale phenomena. We're suddenly using the Doppler effect, which is about light and mechanics, quantum mechanics.
Right. So your question is predicated on the fact that it's really hard to find a quantum theory of general relativity. It's hard to find a quantum theory of gravity. This is true. But the difficulty there, it only comes in certain aspects of that. So what's hard is to understand what happens in extremely high energy or high density situations, like the singularity of a black hole or a big crunch singularity. And it's also hard to write down a framework which is clearly consistent and makes sense and quantizes gravity. But something like the Doppler shift of a photon in an expanding universe, that's not so difficult to analyze with the techniques we have. So for instance, this gravitational time dilation that we discussed, that's an intrinsically general relativistic phenomenon, right? The fact that clocks run faster higher up in a gravitational field than lower down. And you can do that experiment, you can measure that time delay with clocks. You can also do it by beaming light up from, say, a lower elevation to a higher elevation, and you'll see a redshift or a blue shift, depending on which way you beam it. And you can do it with individual photons. That's not at all difficult. And you'll see that each photon is blue shifted or red shifted, just as the beam of light was classically. So there's no problem with quantizing particles in a gravitational field background. The thing that's hard is quantizing the gravitational field itself. So if you tried to quantize gravity waves, the particle would be called a graviton. That we don't really know how to do. Although even there, as long as the effect is weak, as long as you're not very close to a black hole horizon or near a singularity of some sort, we still think we know how to do it. But for quantum particles moving in gravitational fields, there's no real problem.
I actually have two questions. First of all, I want to thank you for your use of analogies the whole way through. It's very helpful. So I'm going to ask for two more analogies. From Hawking's book, one of my takeaways, and I worked very hard on that book. It's just clawed to pieces. It was one concept that there is no fixed physical point in the universe, and there's no fixed time and space. Did I get that right? Or, okay. That was compelling to me. If I got it wrong, just say so. The other question that I'd love for you to take a throw at is, I can understand what a mile is, I can understand what a second is, and 186,000 miles per second really doesn't seem very fast to me in this whole, cosmic universe. Why is there a speed limit? Why can't anything go faster than light? And if you figure that one out, tell Hollywood.
Okay. Yeah, so let's start with the first question. So I think I understand what you're getting at, and it does sound right. So you say there's no fixed point in space, meaning all points in space look more or less the same, or are you talking about the relativity of motion?
The relativity.
The relativity of motion. Yeah. Okay, so you know how, okay, you're on the train, and there's another train next to you, and you have this moment of disorientation where you can't tell if your train is moving or the other train is moving. And it's really disorienting sometimes. And then if it's your train that's moving, you realize you feel some bumps or something, and you can tell. But for that moment, you may not be able to tell. So motion is relative in that sense, even according to Galileo, and then according to Newton, and according to Einstein. There's no absolute notion of rest, right? So we're very used to thinking of one because, well, we live in an atmosphere, and being at rest with respect to the atmosphere, which is usually more or less at rest with respect to the ground, is different than not. I mean, you feel wind or you don't, you're running or you're not. But in outer space, there's only relative motion that matters. And that's true on Earth too. I mean, it's relative motion of you in the atmosphere. It's actually a surprisingly confusing concept, just because we're so rooted in the environment we live in, where it really does seem like there's a rest frame. But yeah, so two trains, you can't tell which one is moving. If you're in a sealed lab and it's not bouncing around, or if it's in outer space, so it's just floating smoothly, you'll never be able to determine how fast you're moving. It just doesn't make sense. It's just how fast are you moving relative to something, and to be able to determine that, you have to be able to interact with that thing. So that's built into basically all theories of physics. Why there's no fixed time? Well, I mean, the universe itself defines a kind of clock. I mean, it's expanding and it's getting less dense. And maybe it'll turn around and recollapse, but for now, at least, it's expanding. But apart from that, there's nothing different about now and tomorrow. I mean, there's no clock built into the laws of physics, just like there's no position or rest frame built into them. Oh, sorry, your other question was speed limit. Yeah. Yes. OK, well, first of all, the speed limit is really in special relativity. And in general relativity, it's still there locally, because according to general relativity, locally inside a small sealed lab, space looks pretty flat. It looks like it would according to special relativity. But it's possible that there could be a way around the speed limit in general relativity because of the curvature. So there's a solution called a wormhole, which most likely doesn't exist and cannot exist, because most likely it cannot be formed. The kind of stuff you need to form it probably doesn't exist. But you can find a solution to Einstein's equations, if I can find them. If you put the correct sort of stuff on the right-hand side of Einstein's equations, anyway, if you put the correct sort of stuff on the right-hand side, you get I'm going the wrong way, aren't I? You get a wormhole solution, which would allow you to move from one place to another very rapidly. There we go. So yeah, if you can put anything you want on the right side, you can get basically anything you want on the left side. But there's a special form of matter, which again probably doesn't exist, but if you put it over here, you produce this solution that connects two distant regions. So that's one way you might be able to beat the speed limit. Why the speed limit is there at all? It's built into the geometry. It's because speed is not exactly the way you think of it. It's not something moving in time, because you have to remember that time and space are linked in this intricate way. So I don't have a very good analogy to explain that, but as you get closer and closer to that speed, your clocks slow down more and more compared to someone who's not moving. And you can keep accelerating all you want, but you'll never exceed that speed as measured by this other person who's just sitting there and not accelerating. So to you, it'll seem like you're accelerating forever, but to them, you'll just get closer and closer to the speed of light and never quite get there. Still, not very much time will pass for you. So you can sort of travel into the future in a way, right? You can go very close to the speed of light. Very little time will pass for you. A lot of time will pass for someone who's not moving. So it's not really like getting around the speed limit, but you can do that. You can come back and find everybody you knew, died a century ago or something. Right? So yeah, I don't know. It seems to be the way the universe is. It's built into the geometry of it. Maybe here.
Okay, you mentioned black holes have mass, spin, and charge. What about magnetic fields?
Good, yeah. A spinning black hole with charge would have a magnetic field. So if you just forget about black holes. If you just have some charge and you move it around, you make a magnetic field. A spinning charged black hole does have a magnetic field too. So yeah, they have electromagnetic fields. There's no, as far as we know, magnetic charges. So those would be called magnetic monopoles. So you don't have the kind of magnetic field which sort of points away from the black hole. You have the kind of magnetic field that a magnet has, which sort of loops around and the field lines come back in. But yeah, a spinning charged black hole would indeed have that, just like a spinning charged ball would. Yeah.
Thank you. Sagittarius A star is being observed soon. Do you have any takes on what is expected to come out of the observations?
Yeah, so it's been observed indirectly in a number of ways already. You can actually image the orbits of stars around it And because it's so heavy and the stars are so close to it, the orbits only take a few years or maybe even a few months. And so people have seen complete orbits, multiple complete orbits of stars. So by the way, I should say for the rest of the audience, Sagittarius A star is the name given to the black hole at the center of our galaxy, of the Milky Way. And yeah, one of the ways we know it's there is by seeing stars orbiting something. It's just like if you saw the planets of our solar system orbiting the sun, but the sun was somehow invisible, you would know it was there. Same thing here. You see stars orbiting it. And so it's clear that there's a very, very heavy object there with mass of about 1 million solar masses, 1 million times the mass of the sun. There is a proposal, I think it's called the Event Horizon Telescope or something, to image it in radio with a resolution that's about its size, if it's a black hole, which almost certainly is. And well, we more or less know what to expect. It should have an accretion disk around it, and so you should see this disk spiraling in. But probably they'll learn something. I'm not a very expert on this, but I suspect they'll learn something about the environment in the interior of the, like right near the center of the Milky Way. I don't think that they'll find anything sort of earth-shattering. I mean, it won't change our conception of black holes, but it will probably teach us more about what's going on in the very centers of galaxies, and maybe it'll help resolve this mystery of how these black holes got so heavy, because there's not a good theory for how a black hole, given the current age of the universe, could have grown to that size. That's actually a big hot topic right now, how that could have happened.
On inflation theory of the universe, can you describe some of the mathematical bases of that, and is it related to quantum mechanics?
Yeah, right. So inflation, in the context of cosmology, is the idea that the universe expanded very rapidly, and more importantly, it accelerated a long time ago. So shortly after the Big Bang, it underwent this period where its expansion rate was increasing exponentially or close to exponentially. So that means in a certain amount of time, it doubled in size. In that same amount of time, it doubled again, doubled again, doubled again, and so on. And so that idea was proposed a long time ago, almost 40 years ago now. It seems to be true in the sense that it makes a set of predictions for what you're going to see when you look closely at very ancient light from the early universe. And those predictions have been confirmed over and over again. But in all that time, no one has come up with a very convincing explanation for what made that happen. Or they've come up with many explanations, none of which is very convincing. Let me put it that way. There's many, many alternative theories of inflation. It's hard to distinguish between them, and it's hard to know fundamentally what was causing it. As for how quantum mechanics comes in, it's sort of like my answer to this other question that you can study quantum mechanics in the background of a gravitational solution, like an expanding universe, and we know how to do that. So we know how quantum mechanics, what role quantum mechanics would play during inflation. What it does is it makes the density of the universe not exactly uniform. Inflation, well, economic inflation sort of equalizes all money, right? Because it makes bank accounts disappear and it makes debts disappear, so everybody has the same amount of money, namely zero, after a while. Same thing happens in cosmic inflation. It spreads everything out, so after a while, the density is the same everywhere. That would be true without quantum mechanics. But quantum mechanics causes fluctuations. It means that the density is not exactly the same everywhere. And those fluctuations in density are the seeds from which galaxies grow later. So when inflation comes to an end, if you have a region that's a little denser than what's around it, it starts pulling stuff in by gravity. It gets denser and denser and denser, pulls more in, and eventually it becomes a galaxy and stars light up and so forth. So quantum mechanics comes into it there. It's actually an amazing story. It means that when you look at the night sky, you're seeing quantum fluctuations that were produced in the very early universe, 14 billion years ago, mapped out for you. So quantum mechanics comes into it in that sense.
Are there actual models that we've used to model inflation?
Yes, yeah, there's if anything, too many of them.
They make them up?
Pretty much, and then they try to test them, and sometimes they fail and sometimes they don't. But there are too many of them that have not failed. So there's a lot that are still alive, let me put it that way. It's hard to constrain them. So I think we can maybe have one more question, or do we need to end now? One more? Okay, one more question. And I think you had your hand up before.
So straying slightly from the topic of today, Sheldon, who apparently had a number of telephone conversations with Stephen Hawking, several years ago abandoned string theory as the unified theory. Was it appropriate for him to do so?
I have to admit, I've only ever seen that show a few times. I'm pretty sure I know who it's based on. It's a guy I was a postdoc with years ago. I won't say who, well, string theory is an interesting story. It was proposed as a theory of the strong interactions, the force that binds nuclei together. And it didn't work for that because it contained a particle like the graviton, like the quantized version of gravity. And so when people realized that, they abandoned it as a theory of strong interactions and adopted it as a theory of everything, as a theory of gravity. Plus, it, by the way, contains lots of other forces. And it's been described as a piece of 21st or 22nd century mathematics that fell into the 21st century. It's really difficult. It's very hard to solve any of its equations. We have a very limited understanding of what it is mathematically. But it seems to have this self-consistency. It is a quantum theory of gravity. It has lots of forces in it that look kind of like the ones in the real world. But then it has more. It has too much stuff in it. And it's really hard to solve these equations. So people lost some steam. I mean, there was a period where it seemed like they were right on the verge of solving these problems, and this was the end of the story. And then they kind of ran out of steam a little bit because, well, things didn't pan out as easily as it seemed like they should. So I don't know. The situation now is that there are still a lot of people who work on it. I'm working on it. I just wrote a paper about a very string theory. It has nothing to do with the real world. It's really about string theory in a very mathematical regime. But I also work on other things. And I think most people who work on string theory these days are like that. They're thinking about lots of problems, and they're interested in it, but they're also interested in other ideas. So yeah, it's not like you have to abandon it or not, right? It's not a monogamous relationship. You can do whatever you want. And you can spend part of your time working on that and part of your time working on something else, and that's fine. Okay, thank you very much. I think we have to end.